All right, folks, let's finish off section 1.3, evaluating limits analytically, part 2. So we're going to jump into the page 2 here and revisit the squeeze theorem a little more formally. So this gray box contains the actual language of the squeeze theorem, and it says the following. If f of x is sandwiched between h of x and g of x, meaning that it's always between the two or equal to the two, for all x that are not equal to c, and c is our value of interest in the limit, if h of x is less than or equal to f of x, which is less than or equal to g of x, for all x not equal to c in some interval containing c, and if the limit of h of x is equal to L, and the limit of g of x is also equal to L, then the limit of f of x also has to equal L. So a fancy way of saying that you can see in this picture is that if the function f is squeezed between two other functions, then, and the limit of those two functions at x equals c is the same, then the limit of the function f at x equals c must also equal L. I mentioned in the previous video that you don't need to know the squeeze theorem or be able to prove it or anything like that. You just need to be able to use consequences of the squeeze theorem. In fact, in terms of using the squeeze theorem, what I did on the previous example was, mathematically, it was pretty sloppy because I never proved to you that this x times sine of 1 over x function is always between the other two. I just kind of graphically looked at it and said, yeah, it looks like it. So that's really not a very rigorous proof of the squeeze or rigorous use of the squeeze theorem. It's really just an illustrative example for you to see how that theorem works. So now let's talk about two big consequences for the squeeze theorem. And the first one I'll mention is this. The limit of 1 minus cosine x over x equals 0. This is one you're going to want to remember. It's important. But this one over here, the limit of sine x over x as x approaches 0, well, I would say if the previous one is important, then this one is really important. And again, these two limits are consequences of the squeeze theorem. We're not going to prove that or see why. We're just going to know that they are. We're going to just take that basically as fact. The second one here that I highlighted, the limit of sine x over x as x approaches 0 equals 1, that limit shows up way more than this one involving 1 minus cosine x over x. So that's why I'm calling it really important. So let's do some examples involving these limits that are consequences of the squeeze theorem. So determine the following limits in example 6. I'll kind of talk through the first one and then I'll sprint through the rest of them, but I want to highlight one thing. So I'm going to write this limit in a different way that perhaps will be more applicable. We'll be able to see it in more applications. Okay, so the limit of sine of n times x divided by n times x as x goes to 0 equals 1 for all real numbers n. So you can plug in anything there for n that's a real number, and that limit will work. Let's just take a look at the graph of sine x over x so we can visualize. So this limit, without looking at the graph, doesn't really mean anything to us. We're just kind of accepting it on fact. But let's take a quick look at the graph. So here I have the graph of sine of n times x divided by n times x. And I've zoomed in here just so we can see what happens around x equals 0, because that's the limit that we're interested in. I've got a slider here for n, so I can take n and rotate or scroll through a couple different values of n there, and you'll see that the graph around x equals 0 looks the same no matter what the value of n is that I choose. And just thinking, from a function standpoint, if x equals 0, then I have the sine of 0 divided by 0. Well, division by 0 is undefined, so we know that this graph really has a hole there at x equals 0. But we can see that the limit, if we ignore everything right here on the y-axis, we approach that value of that height of 1 from the left and from the right, and we do that regardless of what n is. So again, that's just a little quick graphical example to illustrate this important limit that again is a consequence of the squeeze theorem. Okay, so let's go through some examples here. For number 6, part A, the limit of sine of 2 theta divided by theta as theta approaches 0. I've already changed the variable on you. Hopefully you can interchange theta and x and not be confused. Well, in order to use this, the squeeze theorem on this, I need to have 2 theta in the denominator. And the only way I can have 2 theta in the denominator is if I multiply the denominator by 2. Well, I can't just multiply the denominator by 2 because then I change the value of the expression, so I have to multiply both the numerator and the denominator by 2, and that's going to give me the following. 2 times the sine of 2 theta divided by 2 theta. The good news is this is what I need for my limit. So now I'm going to rewrite the limit statement as follows. I'm looking for the limit of 2 times sine 2 theta over 2 theta as theta approaches 0. And to evaluate this limit, I'm going to use that scalar multiple property from the previous page. 2 times 1, because this limit is just 1. And there's my final answer. So on the rest of these examples, I'm going to do some similar algebra to get something of the form sine of n times x divided by n times x. Okay, folks, there you have it. Let me just talk about a couple quick things in here that I think are worth mentioning. In part C, first thing I did was transform tangent into sine and cosine, so the identity function for tangent. And then what we had here was 1 over cosine x times sine x over x. Well, this is a product, and I know that the limit of a product is the product of a limit, assuming that the two limits exist. So what I have here is the sine x over x, that limit is 1, and then for 1 over cosine x, I did direct substitution. So 1 over cosine of 0, the cosine of 0 is 1, so that gives me 1 times 1, or a final limit value of 1. And then in part D, this one's kind of interesting. So I needed to get a 2x in my denominator so that I had a 2x underneath sine 2x. And then I needed to get a 3x in my numerator because I wanted to have 3x over sine 3x. And you might be like, well, wait a minute, the limit says the sine thing has to be in the numerator. Well, this limit can be rewritten as x divided by sine x, because if the limit equals 1, we know the reciprocal also has to equal 1. So then I have this 3x over 3x term to get what I need for sine of 3x. And then by doing a little bit of algebraic manipulation, I move the 2x underneath the sine 2x, I move a 3x above the sine 3x, and then I'm left with 2x over 3x. I just canceled out the x's because we can do that even though the x is in the denominator. We're looking at a limit, so we don't care about canceling out that problem. Final answer here is I have the product of two limits that equal 1 and then times a constant 2/3. So that answer is 2/3. Okay, let's move on. I have another property here, another limit property, and this one's fairly important because it could show up on the AP exam, and it's one you might forget. So I'm In fact, in the years past, I haven't really talked about this one too much, and then it showed up on the 2016 exam, so now I'm making sure that it's incorporated into the notes. Okay, so the limit of a composite function, and hopefully you remember that a composite function looks something like this. We could say f of g of x. That means we're using g of x as the input to the function f, and that's what I mean by a composite function, and you should remember that from pre-calc and perhaps even algebra 2. Okay, so we have a function g of x whose limit as x approaches c, our value of interest. That limit is L, capital L. Well, the limit of f of x as x approaches L has to be f of L. Notice how x is now approaching the limit from the inside function. So if those two things are true, then we have the following. The limit of f of g of x as x approaches c equals f of the limit of g of x as x approaches c. So now this limit is input to the function f, and remember this limit right here was L. So then I basically just have f of L. And let's look at that in an example. Example 7, the graphs of the functions f and g are shown to the right. Evaluate the following limit. The limit of f of g of x as x approaches 1. Okay, so the first thing I have to do is look at the limit of g of x as x approaches 1. So what I've done here is rewritten this problem using the property of limits of composite functions. So I now have the input to the function f, which is the limit of g of x as x approaches 1. Let's take a look at g of x. So we'll notice here that g of x at x equals 1 is defined as 1, but then it has a hole up here at y equals 2. But I don't care about what happens right at x equals 1. All I care about is the limit. So by covering up x equals 1, I can see graphically that the limit of g of x is 2. So I can see that limit graphically. So that means what I'm really doing is looking for f of 2. And f of 2 is 3. Final answer. And again, this is a property of limits, one that you may be tested on in the future. All right, let's go down and look at one last example here. Example 8 says, evaluate the limit of the difference quotient. Remember our friend, the difference quotient. We're going to look at him again. We're going to look at the limit of the difference quotient as h approaches 0. And right now, what I'm asking you to do here seems really abstract. Seems like just, basically algebra work. But trust me, this limit right here has applications in calculus. In fact, half of our year will be applying that limit. Okay, so I'm going to first try direct substitution. Let's see here. We always try direct substitution first. And when I do direct substitution for h equals 0, I have f of x minus f of x, well, that's 0, divided by 0. That gives me 0 divided by 0. And we remember from our previous lesson that that's indeterminate form. We cannot determine the limit from indeterminate form, so we must do more work. All right, so let's see what can we do. Well, I'm going to go ahead and simplify the difference quotient by actually plugging it into the function f. So I have a difference quotient with the actual function square root of x plugged in. Now, there's no simplifying I can do here. I've already tried direct substitution. I can't divide anything out. So the next trick I have is to rationalize the numerator. So multiplying these two expressions, I have to multiply this numerator by this numerator, and that's, again, I don't want to trivialize that. That's a FOIL process, and when I do that, I'm going to get the square root of x plus h times the square root of x plus h, which is quite simply just x plus h. And then I'm going to get, let's see, I have the square root of x plus h times positive root x. Then I have the same thing times negative root x, and that's doing the outer terms and the inner terms, and those two end up canceling. That's the magic of multiplying by the conjugate. That's the step that rationalizes that expression. So the last step I have here is to multiply my two last terms. I have the opposite of root x times root x. Well, that's just minus x. For my denominator, I'm not going to distribute anything. I'm going to keep it separated, keep it expanded, or excuse me, keep it factored. Okay, so when I go to further simplify my difference quotient, let's see, my numerator is x plus h minus x. Well, that just simplifies to h. My denominator, I have h times square root of x plus h plus root x. And then there's where the magic happens. Remember, to simplify a difference quotient, we must get rid of the original h in the denominator, and that's right there. We can cancel that there. So we're left with the following simplified difference quotient. Okay, so there's our simplified difference quotient. And if you had me for pre-calc, when we talked about simplifying difference quotient, I basically just said, hey, this is algebra practice. There's applications of it in calculus, but for pre-calculus work, every time we simplify a difference quotient, it's just practicing algebra. Okay, so why did we learn how to simplify a difference quotient? It's so that we could take a limit, and now we're ready to evaluate the limit. And remember, this simplified difference quotient is exactly the same as our original difference quotient in every single way except at h equals 0, because at h equals 0 we had a 0 in our denominator. So let's go ahead and evaluate this limit. This is a limit that I can evaluate with direct substitution. I'm going to plug in h equals 0 and get the following. And that simplifies to 1 over 2 root x. As I mentioned in the past, sometimes we'll simplify a limit and we won't get just a real number, we'll get an expression in x, and that's because our original expression had both x and h in it. We were looking for the limit as h went to 0, so sometimes we'll still have an x in our expression. Just want to make one more comment about our limit that turned out to be an expression in x. Originally, when I defined limit, I said, hey, the limit has to be a real number. Well, when we end up with an expression in x, we don't violate that informal definition of the limit because x is a real number. So this, one thing I haven't mentioned yet, but AP Calculus AB, we only use real numbers. We don't ever look at imaginary numbers. So x has to be a real number, therefore 1 over 2 root x is also a real number. Congratulations, folks. In a few short weeks, you're going to see the connection between this limit and this function, foreshadowing. Stay tuned.